Hello everyone. Today let's solve the problem number 235, lowest common ancestor of a binary search tree. So what the question states here, let's see. You can just go through the question along with the example. Try to understand the question. I'll just summarize the question so that it will be easier to understand. So what the question states here, we are given a binary search tree. This is important. We are given a binary search tree and two nodes P and Q. You can clearly see here, and we are given a binary search tree and two nodes P and Q. Our task is to find the lowest common ancestor LCA of these two nodes. This is very important. So what is LCA here? So the lowest common ancestor of two nodes P and Q is a binary search tree. In a binary search tree is the lowest node, nothing but the deepest. Here, if we consider this one, 2 and 8 they have given here, right? P and Q. Here, P and Q, the lowest node for these two here is 6. We have only one node, that is nothing but 6. So that's what the output we got here. So that's what we need to display as the output here. You can clearly see that's what they have given. The lowest common ancestor of two nodes P and Q is in a binary search tree is the lowest node deepest in the tree that has both P and Q as its descendants. So here P and Q, here 2 and 8 is the descendants of 6. We can clearly see here. A node can be descendant of itself as well. So in the question they have mentioned a node can be descendant of itself. In this case, if we are considering the first example, then here we can clearly see. First we'll discuss what binary search tree is. In simple terms, binary search tree is, suppose let's consider this node. Every single node, the value of the left subtree to the main node, this one left subtree, this has to be lesser than the value should be lesser than the value of the main node. The value of the right subtree, this value should be greater than the main node. This one has to be lesser, this one has to be greater, right? Same goes with this one. For 2, if we consider here, the left subtree value is should be lesser and the right subtree value should be greater. So this has to be for the every node, right? So every node that we consider, so that is said to be binary, I mean this one, binary search tree. So let's consider the example, same example here. We are given this nodes and P they have given 2 and Q they have given 8, this one. So in the question they have clearly mentioned that the lowest common ancestor of two nodes P and Q in the binary search tree is the lowest node in the tree that has both P and Q as its descendants, right? So here 6 is having 2 and 8 as its descendants. So we need to display 6 as the output here in this case, right? So I hope this is clear. First example. Let's move to the second example. So here they have mentioned this one 6280, this is fine. These are the values, right? And P2 they have given and Q4 they have given here, P and Q, this one, right? So again, so 4 is descendant of 2. So the output they have given here is 2. That's what they have given in the explanation. The least common ancestor of nodes 2 and 4 is 2, since a node can be descendant of itself. So they have clearly mentioned in the question. While mentioning the question also I have said the same thing. So a node can be descendant of itself. So here the lowest common ancestor will be 2 in this case according to the LCA definition, right? So I hope this is clear. Let's discuss the approach first, and then let's discuss the edge cases one by one, and then finally write a code. So I'll just explain the approach here itself. Just give me a second here. So this is binary search tree, right? So what happened to this one? So yeah, this is binary search tree, right? So we can just make use of the this one binary search tree properties to find the LCA, right? So first condition we need to remember here is if P and Q, this one, if P and Q both are less than the root, in this case here, if we consider P and Q both are less than the root, then LCA is left subtree. So suppose this one P and Q both are less than the root here they have given. Suppose it cannot be. In this case, it is not. Let's consider this one here. Suppose if we consider this one here 4. So this is binary search tree. It cannot happen, but still we'll consider if P and Q are less than the root here in this case. So LCA will be, they have given LCA is the left subtree. Suppose we have this one 6. We are just considering here this one 6, 2 and 4 here in this case, right? If P and Q both are less than the root they have given in this case, this is both are lesser than the root. So here the LCA will be in that case 2, the left subtree here in this case, right? So this is first condition. If P and Q are greater than the root, in this case here, suppose let me consider 2 here. Suppose let me consider here 3, and suppose let me consider this one as 4. Here this P is considered P is 3 and Q is 4. Suppose we are just considering this one just for the example sake. So here if P and Q are greater than the root, P is greater and Q is greater than the root here, right? So then the LCA is said to be the right subtree. In that case, LCA will be LCA of P and Q. This one will be the right subtree, nothing but 4 here, right? This is the second case. And finally, otherwise the root itself is the LCA. Otherwise, if these two conditions, whatever I said, if these two conditions if these two conditions are not satisfied, then the root itself is the LCA, because P and Q are on different sides, right? Otherwise, LCA is node itself, or otherwise LCA is root itself. So this is the approach that we'll be going with. So let's discuss the edge cases one by one and then finally write the. So let's discuss the edge cases one by one. First edge case, let's go with one node is ancestor of other. So one node is ancestor of another or other. This is fine. Let me make it easy for you. Let me draw this one here. In this case 6 to 8. So this has to be BST, right? Binary search tree. So this one, let's consider the example one itself. 0, 4, 7, 9. This one will be finally 3 and 5. Suppose P is here 2 and Q is here 8. So this one P is this one we are considering, right? So this is fine here in this case. So here the output will be here 6, as this is the LCA. We have already discussed this one, right, while discussing the approach. So here the output will be 6. This is for the condition one node is ancestor of another. So let's move on with the next edge case when we have only 2 nodes, right? So here let me consider the same example here when we have 2 nodes. Have exactly 2 nodes here. This is fine. Let's consider the same thing here. This will be 7 and 9, and this will be 3 and 5 here. So this will be 2 and Q will be suppose 4, the second one. When we have only 2 nodes, because we know that a node is a descendant of itself. We have already discussed this one in the example. So I'm just taking the same example so that this one will be easier to understand, right? Since here 4 is the right subtree of 2, we can clearly see here 4 is the right subtree of 2. 2 is the lowest common ancestor here. 2 is LCA, nothing but output is 2 here in this case, right? So for the second one, this is for the condition when we have exactly 2 nodes. Let's move on with the third edge case. Nothing but when the tree is highly unbalanced. Suppose here when BST is highly unbalanced, right? Let's consider this example. Let me give here 2 1. In this case, P let me consider 2, Q let me consider here 1. So the output will be 2 here. Why? Here we know that node is a descendant of itself, and for P2 Q1, this one will be the LCA, right, according to the definition. So the output will be 2 here. Since P is the parent of Q, P here, P is the parent right here, Q is left subtree. So since P is the parent of Q, the LCA is 2 itself in this case, right? So this is for the condition when BST is highly unbalanced. So, or we can just consider instead of BST tree, this is not a BST, right? So we don't have the right node, which is the value of the right node, which is greater than the left. So when the tree is highly unbalanced, these three edge cases that we need to consider, right? First one was for this one node is ancestor of another. The second one was for when we have exactly two nodes, and the third one was for when the tree is highly unbalanced. So these are the three edge cases that we need to consider. So next, let's start writing the code. So here let's start writing the code here. The first step is, as we had discussed in the approach, we have to traverse the BST or binary search tree iteratively, right? So I'll just come here. Let me give while of root. Then what we'll do, we are just traversing over this one BST iteratively. So if value of the P is less than the value of the root, and if value of the Q is less than a root value, then we are considering both P and Q are smaller. So we will move the root. We are moving left, right? So I can just write this one in this way. If value of P and Q is less than root dot value. So I'll just give in this way. Sorry. Is less than value of the root, value of the Q less than root dot value of the root. Then what we'll do, both P and Q are smaller in this case. Then we have to move left. I'll just give here root equals root dot left. I hope this is clear. Next step is, if the value of P and Q is greater than root dot value. So we have considered here in this case value of P and Q less than root value. Same thing. Let me consider here. Let me give here else if. So yeah. In this case, both the value of the P is greater than the value of the root and value of the Q greater than value of the root. Then what we will do, both P and Q are larger here. In this case, both P and Q are smaller. So we are moving left. Here in this case, both P and Q are larger. Then we are moving right. So I'll just give here root equals root dot right. This is simple. So else what we will do, we will we have found the LCA node, nothing but root itself. Root is the descendant of itself. Else the root itself we are considering. So I can just give here return root. So this is it. Finally, what we have to do, we have to return null, because if when root is null, this one value is null, right? So we have to return null here. We are going with the 4 conditions here. You can clearly see. One is when root is null, we are returning null. And the second one is when the value of the P and when value of Q is lesser than the root value, then we are moving left, because both P and Q are smaller here. And the third condition is when value of the P and when the value of Q is greater than the value of the root, then both P and Q are larger and we are moving right. So I hope else we know that root is descendant of itself, then we will be considering root itself, right? So if root is null, then we have to return null. So these 4 conditions we are considering here. So I hope the code is completely clear in this case, right? So let's run the code. I hope this works. What happened here? Unexpected end of an input. Did I miss any bracket? So yeah, here I have missed a bracket in the line number 11. Let me give here one more bracket. So let me format this one once and hit the run button again. So you can clearly see here, the sample test cases are getting passed here. So let me hit the button, submit button. So now you can clearly see all the test cases are getting passed here. So the code works absolutely correct in this case. So what will be the time complexity and the space complexity of the code that we have written here? The approach that we went with here is iterative binary search tree traversal, right? So iterative approach or the iterative BST traversal. So what would be the time complexity here? The time complexity would be big of log n, because we are dealing with the binary search properties. So we know that height of the binary search tree in a balanced tree, we can just consider this one for the height of the binary search tree in a balanced tree. So overall time complexity would be big O of logarithmic n here in this case. So I'll just give here big O of log n. So what would be the space complexity here? Overall space complexity would be big O of 1. Why the overall space complexity here big O of is big O of 1, not the big O of n in this case? We are not making use of any constant extra space since we are just making use of the iteration. You can clearly see here. We are going with the approach iterative BST traversal, right? We are making use of the binary search, this one, properties, as we are dealing with the binary search tree. So here overall time complexity would be big of log n, because we are considering height of the BST in a balanced tree. And what would be the space complexity here? Big of 1, because we are not making use of any constant extra space since we are making use of the iteration. So I hope this is completely clear. The solution is completely clear. For now, this is it. Thanks for watching, guys.